Welcome to The Explainer. Today, we're going to tackle a classic statistical puzzle. How can you fairly compare two completely different performances? We're talking apples and oranges here, and we're going to use one of the most powerful tools in data to do it, the bell curve.
Okay, let's just dive right in with a problem. So we've got two runners, Mark and Sally. Now, they both won their annual races, which is awesome. But here's the twist. One of them actually had a slower finish time. So the big question is, who really performed better on their big day?
All right, here are the stats. On the surface, Mark's time of 16.2 minutes is obviously faster. No debate there. But wait a second, look at the context. Sally ran in a much tougher race. The average time was way slower, over 20 minutes. So her performance might have been more exceptional relative to everyone else she was running against. The question is, how do we actually prove that with numbers?
To solve this, we first need to understand the landscape of their data. And it turns out, for many things in the real world, when you graph out all the possible results, they tend to cluster around the average and form a very, very familiar shape.
And this is it. It's called the normal distribution, but pretty much everyone knows it as the bell curve, for obvious reasons. That peak right in the middle, that's the average result. And as you can see, most of the data points are huddled right there in the center.
You know, what's really incredible about this is how often this pattern just shows up in nature. It's almost like a fundamental law of the universe. It describes how things tend to work when randomness is involved.
And I mean, this pattern is absolutely everywhere you look. Human height, IQ scores, even the wild swings of the financial markets. They all tend to follow this bell-shaped pattern. And it's this predictability that makes the bell curve such a powerful tool. So, how do we actually read this thing? Well, there's a really simple rule of thumb that basically acts like a map for the bell curve. And the best part is, it helps us understand the spread of data without any complicated math.
It's called the empirical rule, and all it does is describe how data is spread out from the average using this measure called standard deviation. Just think of a standard deviation as one standard step away from the center.
Okay, so first up, about 68%, so more than 2/3 of all the data points are going to fall within just one of those steps away from the average. This is where the vast majority of outcomes land. Now, if you take two of those steps out from the average, you've suddenly captured 95% of all the data. This is where pretty much everybody is. If you're outside of this range, you're starting to get a little unusual.
And 3 steps out from the middle covers a whopping 99.7% of all the data. This means that any data point that falls beyond this line is incredibly rare. We're talking about a real outlier. And this just illustrates the rule perfectly. Let's take IQ scores. If the average IQ is 100 and one standard deviation is 14 points, then we know that about 68% of all people have an IQ somewhere between 86 and 114. It's as simple as that.
Okay, so we have our map, the 68, 95, 99.7 rule. Now we just need one final tool to solve our runner puzzle. It's called the Z-score, and this is what's going to finally let us compare Mark and Sally on the exact same scale. I want you to think of this formula as a kind of universal translator for data. It takes any single data point, subtracts the average of its group, and then divides it by the size of one of those standard steps. What you're left with is a single number that tells you exactly how many steps away from the average that data point is.
And that's the whole point, right? Z-scores put everything on a level playing field. It just doesn't matter that Mark and Sally ran in completely different races with different averages. The Z-score is going to tell us who is more exceptional within their own context.
So let's do it. Let's calculate Mark's Z-score. We take his time, 16.2, subtract his race's average, 18.2, and then divide by the standard deviation of 2. We get a Z-score of -1.0. That means his time was exactly one standard deviation faster than average.
Now for Sally. We do the exact same thing with her race's numbers. And what do we get? Her Z-score is -1.2. So she was 1.2 standard deviations faster than the average for her race.
And there it is, that's our answer. Since a lower time is better in a race, a more negative Z-score means a more exceptional performance. So even though her raw time was a little slower, Sally's performance, relative to her competition, was statistically better than Mark's.
Okay, this is cool for a running race, but why does any of this really matter? Well, because this exact same logic of understanding what's normal versus what's an outlier is used to make massive decisions everywhere, every single day. This concept is a fundamental tool across so many different fields.
In finance, it's used to model risk, to figure out how far a stock might stray from its average. In the tech world, it powers all those A/B tests that determine if a new button is actually better or if the results are just random noise. Even in manufacturing, it's used to spot defective products that fall way outside the normal range. It's all about separating a meaningful signal from the noise.
In fact, that z-score we just calculated, that's the engine behind a super common statistical test called a z-test. Companies like Statsig use these kinds of tests all the time to figure out if an experiment they ran had a real, statistically significant impact. So, the big takeaway here is that understanding the bell curve helps you see the world more clearly. It helps you spot what's truly average and what's truly exceptional. It gives you a framework for making sense of all the randomness out there. So the next time you see a bunch of data, ask yourself, what's the story the bell curve is telling me?